In the beginning, before the first telescope caught the faintest glimmer of a distant star, before the mind of man conceived of atoms or the fabric of space, there was a darkness so profound, so complete, that it seemed to be the end of thought itself. But within that darkness, unseen, unmeasured, and unmeasurable, lay the vast majority of all that ever was, is, or will be, the matter that shapes galaxies, bends light, and defines the architecture of the cosmos. This is the story of dark matter, the invisible hand that sculpts the universe, the silent architect whose secrets have bedeviled physicists and astronomers for nearly a century. It is a narrative that begins at the edge of sight and reason, where the familiar laws of gravity and motion become spectral and unreliable, and where the known yields to the unknown. Imagine for a moment, drifting outward from our sun, past the planets and the Oort cloud, into the interstellar dark. With each passing light year, the stars thin, the warmth fades, and finally even the faintest glow of the Milky Way is swallowed by shadow. Yet even here, in the loneliest recesses between galaxies, there is a presence, silent, invisible, and immense. The first hints of this unseen presence came not from the instruments of the 21st century, but from the meticulous observations of astronomers in the early 20th. In the 1930s, Fritz Zwicky, a Swiss astronomer working at Caltech, peered into the Coma cluster of galaxies and saw something that defied expectation. The galaxies whirled about their common center with a speed that could not be explained by the mass of their visible stars alone. By applying the virial theorem, a mathematical expression relating kinetic and potential energy, Zwicky concluded that the cluster must contain far more mass than was visible. He called this missing component dunkle Materie, dark matter, a phrase that would haunt astrophysics for decades to come. Zwicky's calculations were dismissed by many as an artifact of imprecise measurement, a curiosity rather than a revelation. Yet as the decades passed, the evidence only grew. In the 1970s, Vera, Rubin, and Kent Ford turned their attention to the rotation curves of spiral galaxies. According to Newtonian mechanics, the stars and gas in a galaxy should orbit more slowly, the farther they are from the center, just as planets in the solar system orbit the sun in accordance with Kepler's laws. But Rubin's careful measurements showed something astonishing. The rotation curves of galaxies were flat. Stars at the edge of the disk orbited just as quickly as those near the center, defying the expected drop-off. The only explanation was that each galaxy was surrounded by a massive, invisible halo of matter, dark matter, whose gravitational pull kept the stars racing in their orbits. This was no longer an isolated anomaly. The cosmic ledger was imbalanced on every scale, in clusters, in galaxies, in the great web-like filaments that stretch between cosmic voids. The cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, revealed subtle fluctuations, acoustic peaks and valleys, whose very shape could be read as a ledger of the universe's total mass and energy. The results were unambiguous. The vast majority of matter in the universe is dark. Yet what is this darkness? What is it made of? The question is as profound as it is vexing. The ordinary matter that makes up stars, planets, gas, and dust, what physicists call baryonic matter, accounts for a mere 15% of all matter in the universe. The rest is dark matter, unseen, undetected, inferred only by its gravity. It does not emit, absorb, or reflect light. It neither glows nor dims. It is, in every way that matters to our senses, invisible. The search for dark matter is a journey through the most arcane corridors of physics. It is a story of ingenious experiments, of deep underground laboratories, of satellites drifting through the silent night, of detectors cooled to near absolute zero in the hope of catching the faintest whisper of a passing particle. It is a story of failure and hope, of theories that shatter on the anvil of experiment, of new ideas rising from the ashes of the old. The leading candidate for dark matter is the weakly interacting massive particle, or WIMP. Born from the fertile imagination of particle physicists in the 1980s, the WIMP is a hypothetical particle that interacts via the weak nuclear force and gravity, but not via electromagnetism or the strong force. WIMPs are massive, hundreds or thousands of times heavier than a proton, but so feebly interacting that trillions pass through every human body each second, unnoticed and unhindered. The allure of the WIMP is not merely its ability to explain galactic rotation curves or the cosmic microwave background, but its natural emergence from theoretical frameworks like supersymmetry. Supersymmetry, a bold extension of the standard model of particle physics, postulates that every known particle has a heavier, as yet undetected partner. The lightest supersymmetric particle is stable, massive, and weakly interacting, a perfect candidate for dark matter. In the early universe, WIMPs would have been produced in abundance, their annihilations and decays shaping the cosmic balance sheet. As the universe expanded and cooled, the WIMPs would have frozen out, leaving behind a cosmic relic, the dark matter that permeates space today. To detect a WIMP is to attempt to catch a shadow. Deep beneath mountains in Italy, in the tunnels of the Gran Sasso Laboratory, the Xenon experiment waits for the faintest flicker of energy, a nuclear recoil, from a passing WIMP colliding with a xenon atom. In the old Homestake gold mine in South Dakota, the Lux Zeppelin experiment sits in silence, its tank of liquid xenon shielded from cosmic rays by a mile of rock. These detectors are miracles of engineering, capable of sensing minute flashes of light or tiny ionization trails, but so far, they have found nothing. The universe, it seems, keeps its secrets well. As the years have passed and the null results have mounted, physicists have begun to look beyond the WIMP. Perhaps dark matter is not massive but light, an axion, a ghostly particle first proposed in the late 1970s to solve a puzzle in quantum chromodynamics. Axions, if they exist, would be so light as to be almost massless, but their sheer abundance could account for the missing mass of the universe. Experiments like ADMX in Washington state search for axions by looking for the faint conversion of these particles into photons in a strong magnetic field. The search is delicate, slow, and so far inconclusive. Or perhaps dark matter is not a particle at all, but something stranger. Some theorists have suggested that dark matter could be primordial black holes, relics from the earliest moments of the universe, formed not from collapsing stars but from quantum fluctuations in the very fabric of space and time. These black holes would be small, perhaps the mass of an asteroid or a mountain, but they would be invisible except for their gravitational pull. Gravitational lensing surveys, such as those conducted by the Macho and Eros collaborations, have searched for the telltale signs of such objects, but the results suggest that primordial black holes, if they exist, cannot account for all the dark matter. There are those who have questioned whether dark matter exists at all, or whether our understanding of gravity is simply incomplete. Modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in the 1980s, suggests that at very low accelerations, gravity behaves differently than predicted by Newton or Einstein. In this view, the flat rotation curves and the motions of galaxies can be explained without invoking invisible matter. MOND and its successors, such as TVS and emergent gravity, have had some successes, particularly at galactic scales, but struggle to explain the full array of cosmological data, particularly the cosmic microwave background and the large-scale structure of the universe. For most physicists, dark matter remains the more compelling explanation. Yet if dark matter is real, it must leave traces, however faint, in the world we can see. One of the most compelling lines of evidence comes from the phenomenon of gravitational lensing. As predicted by Einstein's general theory of relativity, gravity bends the path of light. When a massive object, such as a galaxy cluster, lies between a distant quasar and the Earth, its gravity warps the intervening space, distorting and magnifying the light that passes through. In some cases, this produces multiple images, arcs or rings, the so-called Einstein rings. By mapping these distortions, astronomers can measure the total mass of the lensing object, regardless of whether it emits light. Again and again, these studies show that most of the mass is invisible. Perhaps the most striking example comes from the Bullet Cluster, a pair of colliding galaxy clusters located 3.7 billion light-years from Earth. In 2006, a team led by Douglas Clough used data from the Chandra X-ray Observatory and the Hubble Space Telescope to map the distribution of ordinary matter and total mass in the cluster. The hot gas, comprising most of the ordinary matter, was slowed and heated by the collision, emitting bright X-rays. But the gravitational lensing map showed that most of the mass had passed through the collision unimpeded, separating cleanly from the hot gas. This separation is precisely what one would expect if the majority of mass is in the form of collisionless dark matter rather than modified gravity. The bullet cluster stands as a cosmic smoking gun, a direct glimpse of dark matter in action. To contemplate the role of dark matter is to confront the profound strangeness of the universe. Every galaxy, every star, every atom of your body is embedded in a vast halo of dark matter, an invisible scaffold that holds the cosmos together. Without it, galaxies would fly apart, stars would never condense, large-scale structure would dissolve into chaos. The universe would be a very different place, sparse, lifeless, unrecognizable. Yet this darkness is not merely a backdrop, a passive stage upon which the drama of luminous matter is played out. It is an active participant, shaping the evolution of the cosmos from the earliest moments. In the aftermath of the Big Bang, as the universe cooled and expanded, tiny quantum fluctuations were amplified by gravity, seeding the formation of structure. But ordinary matter, coupled to light, could not clump until after the universe had cooled enough for atoms to form. Dark matter, immune to the electromagnetic force, began to collapse and cluster much earlier, forming the gravitational wells into which ordinary matter would later fall. The great cosmic web, the network of filaments and voids that defines the large-scale structure of the universe, was woven by dark matter, its threads invisible but essential. The search for dark matter is more than a scientific quest. It is a meditation on the limits of knowledge and the nature of reality itself. We are creatures of light, evolved to see and sense the luminous. Our theories, our instruments, our very language are tuned to the visible. Yet the cosmos humbles us, reminding us that the visible is but a tiny fraction of what is. In the words of the poet Rainer Maria Rilke, the visible is only the skin of the real. Theories abound. Some physicists have proposed that dark matter may consist of sterile neutrinos, elusive cousins of the known neutrinos, particles so ghostly that they do not interact via the weak force, but only through gravity. These sterile neutrinos could be produced in the hot, dense early universe, and might decay, emitting faint X-rays that could, in principle, be detected by sensitive telescopes. In 2014, a tantalizing signal, a faint X-ray line at 3.5 keV, was reported in observations of galaxy clusters, sparking hopes that it might be the signature of decaying sterile neutrinos. Yet subsequent observations cast doubt on this interpretation, and the mystery remains unresolved. Other theories venture into even stranger territory. Some have suggested that dark matter could be composed of entirely new forms of matter, bound by new forces, forming so-called dark sectors. These hypothetical particles might interact with one another via dark photons, analogous to the photons of ordinary electromagnetism, but invisible to us. Such dark sectors could be as rich and complex as the visible world, with their own chemistry, structure, and perhaps in the wildest speculation, their own forms of life. The possibility that dark matter consists of entire families of particles, fields, and interactions, an entire shadow universe intertwined with our own, has inspired both awe and skepticism. It is a reminder that the standard model of particle physics, for all its triumphs, is incomplete. The standard model cannot explain the mass of neutrinos, the asymmetry between matter and antimatter, the nature of dark matter, or the dark energy that drives cosmic acceleration. Each mystery is a crack in the edifice of understanding, an invitation to deeper inquiry. The search for dark matter has driven the construction of vast instruments and global collaborations. At CERN, the Large Hadron Collider smashes protons together at energies of 13 TeV, probing for signs of new particles that might reveal themselves via missing energy, events where something invisible carries away momentum. So far, the LHC has found no conclusive evidence of supersymmetric particles or other dark matter candidates, but the search continues, pushing to ever higher energies and more sensitive detectors. In space, the Alpha Magnetic Spectrometer, mounted on the International Space Station, searches for signs of dark matter annihilation, high-energy positrons or antiprotons that might be produced when dark matter particles collide and annihilate each other. The Fermi Gamma Ray Space Telescope scans the center of the Milky Way for excess gamma rays that could be the fingerprints of such annihilations. Both have reported intriguing hints: an excess of positrons, a faint gamma ray glow, but nothing that rises to the level of discovery. The cosmos, it seems, is a master of ambiguity. Meanwhile, new ideas proliferate. Perhaps dark matter is not cold and slow-moving, as in the standard cold dark matter (CDM) model, but warm or even hot. Warm dark matter, consisting of lighter particles such as sterile neutrinos, could suppress the formation of small-scale structure, potentially resolving some tensions between simulations and observations of dwarf galaxies. Alternatively, perhaps dark matter is self-interacting, capable of colliding and scattering with itself, altering the density profiles of galactic halos and addressing discrepancies in the cores of galaxies. Each theory is tested against the growing wealth of astronomical data, the distribution of galaxies, the structure of clusters, the patterns in the cosmic microwave background, the properties of dwarf spheroidal galaxies orbiting the Milky Way. Simulations, running on supercomputers, attempt to model the growth of structure from the earliest times to the present day, adjusting the properties of dark matter to match the observed universe. The results are sobering. No single theory fits all the data perfectly. The universe, it seems, is both more complex and more subtle than our models can capture. Yet the search continues, driven by curiosity and the conviction that the universe is knowable. New experiments are being planned and built. The Super CDMS experiment at Snow Lab in Canada, designed to detect low-mass dark matter particles. The LZ experiment in South Dakota, aiming for unprecedented sensitivity to WIMPs. The next-generation Axion telescopes, probing deeper into the parameter space. In space, the Euclid and Nancy Grace Roman space telescopes will map the distribution of dark matter with exquisite precision, using gravitational lensing to trace the invisible scaffolding of the cosmos. To understand dark matter is to understand the fate and origin of the universe. The dark matter halos that surround galaxies and clusters are not static, but dynamic, shaped by mergers, collisions, and cosmic flows. In clusters, dark matter can be stripped away, forming tidal streams and substructure. In galaxies, dark matter governs the formation of stars, the growth of black holes, and the assembly of disks and bulges. Without dark matter, there would be no galaxies, no stars, no planets, no life. The darkness is not merely a lack of light, but a presence, a force, an actor in the cosmic drama. It is the silence in which the music of the spheres is played, the canvas upon which the stars are painted. It is both a mystery and a promise, a reminder that the universe is vaster, stranger, and more beautiful than we can imagine. Yet the search for dark matter is not only a scientific quest, but a human one. It is a story of perseverance, of hope in the face of uncertainty, of the willingness to confront the unknown. It is the story of men and women who have devoted their lives to the pursuit of a shadow, who have built machines of exquisite sensitivity and braved the depths of the earth in search of a fleeting signal. It is a story of community, of collaboration across continents and cultures, united by a common desire to know. In the quiet depths of the Gran Sasso laboratory, scientists gather in the dim light, monitoring the readouts from the Xenon experiment. Each blip, each faint pulse of light is scrutinized, analyzed, compared against background noise. Months pass, then years. Funding is uncertain, careers are at stake, yet the search continues. There is a kind of faith at work, a belief that the universe is intelligible, that its secrets can be wrested from the darkness. In the control rooms of the Large Hadron Collider, physicists pore over data, searching for signs of supersymmetry, of missing energy, of new physics beyond the standard model. The results are ambiguous, the signals elusive, yet the search continues. There is a sense of humility, of awe in the face of the unknown, but also of fierce determination. In the deserts of Chile, at the Atacama Cosmology Telescope, astronomers map the polarization of the cosmic microwave background, searching for the subtle fingerprints of dark matter in the early universe. In the chill of the South Pole at the Ice Cube Neutrino Observatory, detectors buried deep in the ice await the passage of high-energy neutrinos, searching for clues to the nature of dark matter. The search is not without its disappointments, its reversals. Promising hints vanish under scrutiny. Anomalies dissolve into statistical fluctuations. Theories rise and fall. Yet each failure is a lesson, each setback a step on the path to understanding. In the words of Isaac Newton, If I have seen further, it is by standing on the shoulders of giants. The search for dark matter is the latest chapter in a story that stretches back to Galileo, to Newton, to Einstein. A story of wonder and discovery. To ask what dark matter is to ask what the universe is made of, and by extension, what we are. The atoms in our bodies, the light from the stars, the dust in our lungs, all are but a tiny fraction of what exists. The rest is darkness waiting to be understood. It is a humbling, exhilarating thought. Some have speculated that dark matter may play a role in the origin of life itself. In regions where dark matter density is high, such as the centers of galaxies, its annihilation or decay could inject energy into the surrounding gas, altering the conditions for star and planet formation. In the early universe, dark matter may have acted as a catalyst, enabling the first stars to form and light up the cosmos. Without dark matter, the universe would be dark in every sense. No galaxies, no stars, no life. The darkness may also hold the key to the universe's ultimate fate. As the cosmos expands, the density of dark matter decreases, but its gravitational pull continues to shape the destiny of galaxies and clusters. In the far future, as the stars fade and the galaxies drift apart, the dark matter halos will persist, silent witnesses to the passage of eons. The darkness endures, even as the light dies. Yet for all its power, dark matter remains elusive. It is a presence felt but never seen, a shadow that shapes the world but refuses to be named. It is the greatest unsolved mystery in modern physics, a puzzle that challenges our understanding of matter, energy, and the nature of reality itself. The search for dark matter is a journey without a map, a quest whose end is unknown. It is a reminder that science is not merely a collection of facts, but a way of being in the world, a willingness to ask questions, to embrace uncertainty, to press against the boundaries of the known. It is, in the end, an act of faith. Yet the darkness is not absolute. At the edge of knowledge, there is always a glimmer, a hint, a whisper, a possibility. In the silence between the stars, in the invisible scaffolding of galaxies, in the faintest pulse of a detector deep underground, there is hope. The universe is vast, and its secrets are many, but the search goes on. In the words of the cosmologist Vera Rubin, whose work did so much to reveal the existence of dark matter, science is competitive, aggressive, demanding. It is also imaginative, inspiring, uplifting. The search for dark matter is all these things, a contest of ideas, a test of ingenuity, a leap into the unknown. The universe is not only stranger than we imagine, but stranger than we can imagine. Dark matter is the embodiment of that strangeness, the shadow that haunts our dreams of understanding. It is the darkness at the heart of the world, the silent companion of every star and planet, the unseen architect of all that is. We are children of light, but we are born of darkness. The atoms in our bodies, forged in the hearts of stars, owe their existence to the invisible hand of dark matter. The galaxies, spinning in silent grace across the sky, are held in place by a presence we cannot see. The universe is a tapestry woven of light and dark, of the known and the unknown. To search for dark matter is to search for ourselves, to ask what it means to exist, to know, to wonder. It is a journey without end, a question without a final answer. Yet it is a journey worth taking, for in the darkness we find not only mystery but possibility. The universe is vast, the darkness deep, but the light of curiosity endures. As the night deepens and the stars wheel overhead, the search continues. In laboratories and observatories, in deserts and mines, in the quiet spaces between thought and dream, men and women keep watch, listening for the faintest whisper from the darkness. The universe waits, patient and silent, its secrets intact. Yet in the heart of that darkness there is hope, a hope as boundless as the cosmos itself. The hidden heart of the cosmos beats in silence, its rhythm felt in the rotation of galaxies, the bending of light, the birth of stars. Dark matter is the shadow that defines the shape of the world, the unseen hand that guides the dance of creation and destruction. It is the darkness within which the universe is born and dies, the mystery that gives meaning to the search. In the end, perhaps it is the mystery itself that matters most, the recognition that the universe is not ours to master, but to wonder at. The darkness is not an absence but a presence, not a void but a promise. It is the invitation to seek, to question, to dream. So the search goes on in laboratories and mines, in the silence of the night and the brightness of day. The darkness endures, but so does the light of inquiry, of hope, of imagination. The universe is vast, and its secrets are many. Yet in seeking the darkness, we discover the light within ourselves. And so, as the stars wheel overhead and the night grows deep, the story of dark matter continues. A story written in shadows, in silence, in the unending dance of light and dark. The search is not over, the answer is not yet known, but the journey, as always, is its own reward.